Today I will present the vector quantization scheme using LBG. So in this project, the goal is to compress the weight vectors of a convolutional neural network. The two theta matrices are given and it's being generated from the MATLAB code. The goal is to utilize the LBG algorithm to compress the two weight vectors and generate the codebook vectors. So at a high level, the LBG algorithm performs the following. Starting with the initial set of codebook vectors are either pre-trained or predetermined, and you can pick a distortion threshold epsilon. And afterwards, each weight vector is mapped to the closest proximity center mass based on the average codebook vector, and the average distortion, which is the Euclidean distance between the codebook vectors and the weight vectors, is determined. And this process is keep repeating up until the quantization error, which is if the quantization error is less than the threshold epsilon, then the process is stopped. So for this particular project, I've chosen the epsilon value to 0.00001, and the codebook size is the code is implemented in a way such that the codebook size can be chosen, and we can find out which size is the most optimal that have the lowest distortion values and the highest compression ratio. So the theta 1 and theta 2 weight matrices are given and generated from the MATLAB code, but it's in a double floating point format. Eventually they will be quantized to int 32, int 16, int 8, and int 4 format via the following Python script. The entire project is implemented using Python. So theta 1 has a huge dimension of 25 rows and 401 columns. Theta 2, on the other hand, has 10 rows and 26 columns. So each matrix shall be divided into 2 by 2 sub-matrices. So it's going to be 4 elements vectors. The codebook will be trained to give the best estimates of these 2 by 2 sub-matrices. Since theta 1 has really odd dimension of 25 and 401, we cannot split it evenly with the 2 by 2 submatrix. So what happened is now we will trim off the column 0 and the row 0 by taking the average of row 0 and row 1 and augment it to become one row, and column 0 and column 1, and augmented that into one column. So that will reduce the dimension of theta 1 to 24 by 400. So the implementation of the algorithm is firstly we choose an arbitrary value of epsilon. Firstly, the initial code vector is determined by taking the average vector of the input weight matrix, and this code vector is added to the codebook. So we don't start with a full size of codebook. We start with just one initial code vector, which is the average of the entire list of the weight matrix. And from this initial code vector, we will generate 2 new sets a new set of two code vectors, which is based on the initial average. The way that we reach these a set of two code vector is that we take the initial average vector and we multiply by a factor of 1 plus epsilon, and the second will be multiply by the initial average vector with 1 minus epsilon, so that it diverge. So the codebook size can vary, and what happens is that each of the code vectors will generate another two code vectors, and that the initial average vector will be replaced by these two code vectors. And the next step is that we will train these two code vectors to have a better center mass or proximity to the rest of the input weight vectors. So the next step, and step 3, we will map each of the codebook vectors generated above to the closest proximity set of input weight vectors. So the distance is determined by the mean square error, which is a Euclidean distance. The codebook is iterated over, and a new center mass is recalculated for each vector. And the codebook will be updated by replacing the old code vectors from step 2 with the new center mass. So from a set of two vectors from the step above, we replace it with another two vectors, and each of them is a new center mass of two chunks of the input weight vectors. We will calculate the average distortion between the codebook vectors and the corresponding proximity weight vectors, and determine the quantization error. If it's less than the epsilon threshold, we continue to step 5. Else we will reiterate step 3, and we will keep finding the center mass. So the vector will be trained to get closer and closer to the input weight vector. For step 5, based on the given codebook size, we will check if the number of code vectors inside the codebook has reached the desired codebook size. If not, then we kind of go back to step 2, where each of the code vectors inside the codebook will get regenerate into two. Will get split into two code vectors. And each of the code vectors is nothing but the old code vector multiplied by a factor of 1 plus epsilon, and the second one will be the old code vector multiplied by a factor of 1 minus epsilon. So we would have the codebook size in total will be a power of 2, because each of them will essentially spawn 2 code vectors. So each old code vector will spawn 2 new code vectors. So the next portion we have is we can kind of visualizing the LBG implementation for each iteration. So for the first several iteration, as you can see, the red dots represent the code vectors, and the black dots represent the input data. So it's nothing but the average. So it's kind of like in the middle. And for each iteration we train, the set of code vectors, which is the red ones, tend to get closer and closer to the black one. And then at the end, when we reach the number of size or the error has less than the epsilon values, then we can kind of see that the code vectors is pretty close and encapsulate the kind of mimicked the compares weight. It kind of mimic the original input weights. Yeah. So this graph represents where the code vectors lies in that huge chunk of data It actually lies in the middle where the data is most concentrated. The above graph is the compression weight, So the compressed weight is trying to converge as much as possible to the actual data. As for the codebook vector, it is in between the center mass of the input data. Oh, yeah, so the next step in the design is to determine the most optimal codebook size. So I ran a bunch of experiments with the codebook size varies. This is log of to power 2 of the codebook size. So if essentially I ran the experiments on a codebook size of 2, 4, 8, 16, and 32. And we can kind of see that the average distortion decrease as the codebook size increase. And the compression ratio, it's increased a bit for a codebook size of 4. And then after 4 and actually, yeah, and it is kind of plateau between 4 and 8, but after 8 is decreasing for the compression ratio. Yep. Codebook size, average distortion. Oh, the above is from the graph for theta 2 and the below graph is for theta 1. So the optimal values for the codebook size is 8 because that one generally kept the compression ratio at high at reasonable values and the distortion low. So the simulation result is based on the codebook size of 8, and so I generate the codebook for each data type int 32, int 16, int 8, and int 4. And then the codebook has been converted back to floating point for comparison purpose. So for theta 1 is int 32, int 16, int 8, and int 4. And the average distortion, it's a bit difficult to visualize because the distortion at int 4 is pretty huge, and 8 is also huge comparing to like 16 and 32. So if we eliminate the point where it's so huge that even like log if you take the log, it cannot represent it. You cannot see it in the graph. So you can kind of see that in 32, this is log 2, so 2 to the 5 is 32. It has a really low distortion, so that's as expected. So for theta 2 result, I also went through the same process of int 32, int 16, int 8, and int 4. And the distortion is kind of, the graph is kind of similar, it has a similar behavior. Int 4 and int 8 has a really big distortion as compared to int 16 and int 32. So yeah, regarding the compression ratio, so for theta 1, since theta 1 has a huge dimension and it has 25 times 401 entries, the compression ratio is actually kind of big for theta 1. If we implement the int type that's 4 and 8, you have a benefit of a high compression ratio. But for theta 2, compression is a bit smaller, like by a factor of 10 comparing to the theta 1 because of the size of theta 2. So yeah, so the more we have, the more bits that we have in our data type, so like type 32 or type 16, we have a lower compression ratio. So the appendix contains the actual Python code that I've implemented. And that's pretty much it for the presentation. Yeah, thank you for your time.